Okay, got it. Yeah. So I believe today it'll be a double header. I'm not sure. Let's see how it goes. John Hennessy and Shule Nixart, but certainly starting with John. And I wanted to, but initially I was a little confused that there was a talk that Shule was giving, so I prepared some introduction for Shule, but we'll do that later. When I realized John's giving the talk, I said, well, I mean, I know John in the sense interactive thing on the UX project, but I really didn't know much about John at all. So I did what people do these days. You go into Google and you type in John Hennessy, and I put JPL just initially, and then I got a company that is called Lead 411, and it says a CEO, NASA Jet Propulsion Lab. I said, wow, I didn't know that John. I knew John worked at JPL. I didn't know he was the CEO. But then I checked again, and every time you type in this lead411.com, it gives you all the details, but the description keeps changing. But anyway, that was not so. But then I found there's a John Hennessy who's actually very well known. He's the founder and CEO of Hennessy Special Vehicles. And he's far better known than our own John Hennessy, but he doesn't know much about things that our John Hennessy knows, which is on atomic layer deposition, atomic layer etching, ultraviolet sensors, semiconductor surface passivation, all sorts of magic that allow essentially high quantum efficiency to be realized for sensors. It's one thing for when the photon gets in to get a photoelectron. The trick is to get the photon in. If you can't get it in, it doesn't matter what is your internal QE, and that's where John is a star. He finished his PhD at MIT in electrical engineering, and gradually has gone into what I call as astroengineering. And today we'll hear on anti-reflection coatings and other things from John. Welcome to the UV Club, John.
Great, thanks a lot. Thanks for the intro. There's another famous John Hennessy too that was president of Stanford, who was also an electrical engineer, but that is also not me. And apologies for the confusion. Originally, we were going to try to do this as a double header talk, as Shri mentioned, with Cholet talking about delta doping and myself covering coatings, but we decided to just give it all a single shot here. And so I'll try to cover all of these topics that all have to do with improving the sensitivity of ultraviolet observations. So going from detectors to some of the coatings and filters that we put on detectors, and also talking a little bit about the work that we're doing on mirror coatings for the UV. So let's see how this goes. So first, just for those that aren't familiar with JPL, Cholet and myself are part of a section that's called the Micro Devices Laboratory at JPL. It's within the instruments division there. MDL is essentially an end-to-end microfabrication facility that is composed of many groups with different specialties. Some of these groups have core competencies in things like submillimeter detectors and lasers, diffractive optics. Our group is the ultraviolet visible detectors and systems group, all of the members of which are listed on the right here. And we sort of bring together a team of people with different specialties in detector fabrication, in device physics, in chemistry, in astronomy, kind of all the aspects that you need to build an ultraviolet system. So I'll definitely thank all of the people listed here. All of the slides that you'll see coming up have been pulled in one way or another from contributions of all these people. And I'll also mention that a lot of our work is done in collaboration with industry and academia, and I'll try to acknowledge them as we go. Of course, the club here is predominantly interested in instrumentation for astronomy, and that drives a lot of the efforts within our group at JPL. And so we're interested in developing the detectors and coatings that I'll be describing to meet the needs of various NASA-related missions, ranging from suborbital balloon or sounding rocket missions to more recently CubeSats, and then hopefully in the near future, things like Explorer and Discovery missions and large strategic flagship missions. We also work on a lot of technologies that maybe don't have immediate NASA applications, but are of interest for medical and diagnostic imaging, or semiconductor inspection, or high energy physics, some of which I'll talk about as we go. The theme is going to be how can we improve the efficiency of ultraviolet instrumentation? And so I tried to capture the deficiency that's seen in typical orbital space UV instruments by just taking a few examples from the COS instrument on the Hubble Space Telescope, for example, and the GALEX instrument, which operate with peak efficiencies in the single-digit percentage. This is in great contrast to systems which operate at visible or near infrared wavelengths, where efficiencies near or above 50% are fairly common. So there's a pretty big gap here in overall instrument performance. But the takeaway is that even moderate component level improvements can result in large increases in system throughput. Some of this will happen with the detector technologies that I'll talk about. Some is possible with the filter and coating technologies as well. The theme along the way is going to be that there's a lot of materials challenges in the UV, and ultimately that's why these efficiencies historically have been so low. So we'll start with the detectors. A lot of this aspect of the talk is sort of a natural follow-on to the talk that Roger Smith gave a couple of weeks ago. If you didn't hear that, I'd invite you to go back and listen to that talk after this one. He introduced a lot of the sensor and detector architectures that are considered for ultraviolet sensors. And so I won't be going as much into the sort of device architecture aspects of detectors like CCDs and CMOS imagers, but talk instead specifically about some of the processing that we're doing to improve the ultraviolet efficiency of these systems. So as Roger mentioned, if you take a silicon imaging sensor like a CCD or a CMOS sensor, there's a lot of electronics and front surface structures that would prevent you from using a front illuminated sensor in the UV, since those materials would absorb all of the photons that you're interested in. So you need to flip the detector around essentially and illuminate from the backside. If you do that with virtually any standard CCD or CMOS imager, you'll get a quantum efficiency curve that looks like the one I'm showing on the right here, that has high quantum efficiencies at visible wavelengths and then rapidly falls off as you move into the UV with little to no response below 200 to 300 nanometers. And this has everything to do with the plots I'm showing on the left here, which highlight the absorption depth of photons in silicon as a function of wavelength. So at long wavelengths, these absorption depths can be in the micron range. As we go into the UV, they fall all the way into the nanometer range. And that's a problem because of the issue associated with the silicon interface. So silicon is a great material, and you can easily get a silicon wafer, for example, that has impurity levels in the parts per trillion, which is pretty amazing, with crystalline defect densities that have similar macroscopic scales. But that periodicity and perfection essentially ends once you get to the backside of the detector. So you run out of silicon atoms. This is the dangling bond problem. It's not literally a dangling bond in the sense that the silicon is typically bonded to something like oxygen or hydrogen or carbon, but the breaking of the periodicity in the lattice leads to the presence of interface states which can trap charge. And so what ends up happening is the accumulation of this trapped charge bends the conduction band and valence band energies as a function of depth from the surface, and you create a potential well that ultimately will trap charge carriers that are generated in the vicinity of the surface. And so that means for those ultraviolet photons that get absorbed in just the first few nanometers of the silicon, instead of moving down into the detective part of the sensor, they fall back and get trapped in this well. And so that's the dead layer problem. So I'll talk about how we fix the dead layer problem, but I'll first mention that if you don't address this problem in a fundamental way, it can lead to other basically issues in operating back illuminated silicon devices. These are all CCD sensors here from various space instruments showing effects like quantum efficiency, hysteresis, and radiation-induced damage that essentially is related to variations in interface state trap density as a function of either radiation, as a function of time or temperature that cause, in some cases, permanent changes to the efficiency of your device. And so it's not only a matter of improving the quantum efficiency, which I'll talk about, it's also a matter of improving the stability of back illuminated devices. So how do we do this? To get rid of the potential well that would naturally occur at the backside of a silicon sensor, we essentially introduce charge at the back of the detector. And that charge is introduced by growing a new silicon lattice that has a really high concentration of dopant atoms added to it. This counteracts the charge that would occur from those dangling bonds and bends the bands back in the direction that you want in order to promote the collection of charge carriers that are introduced right at the surface of the silicon. And so this is called delta doping, as originally conceived, because these dopant layers essentially appear as a delta function in the growth process that's used for this fabrication. I'll talk a little bit more about this molecular beam epitaxy approach. Some of the important considerations here are that this structure that we're creating on the backside of the device is also only a few nanometers thick. So we're still compatible with the very shallow absorption depth of the ultraviolet photons. And so by eliminating that potential well, you also sort of eliminate some of those stability issues that were highlighted on the last slide. So not only do you recover the quantum efficiency that is lost in a normal front or back illuminated CCD, you also get this improved stability. And so I'm showing here just some quantum efficiency measurements of a CCD, in this case with no coating, that now shows 100% internal quantum efficiency. In other words, it matches the limit of the natural silicon reflectance throughout all of the UV and extending even into the EUV and soft X-ray regime ultimately. So here's sort of maybe a more intuitive way to describe the overall process. Again, if you take a cross-section of a CCD or CMOS imager, you have your contacts and electrodes on the front side. You have the photosensitive volume, which was described in detail by Roger's talk a couple weeks ago. And then typically a thick photo-insensitive substrate on the backside of the wafer. So front side illumination won't work for the UV, which we described. If you want to illuminate from the back, you generally need to remove most of that insensitive thick silicon wafer. So there's a thinning processes that are involved in the fabrication of these devices, but you're still left with this dead layer at the back of the device. So again, you'll lose charge carriers generated right at this backside. But then this delta doping passivation essentially creates now a favorably energetic profile such that charge carriers can now be detected. There's the additional benefit that by introducing such a high doping concentration to the backside of this device, it's now electrically conductive as well. And that means you can do things like apply a bias to basically improve the depletion of your photosensitive volume. So this can be important both for thin sensors in this range of 15 microns, but also thicker devices as well, where it might be hard to otherwise fully deplete this volume, and give it basically an additional energetic push to these charge carriers and really make sure that they're detected. And then later I'll talk about collecting those photons that would otherwise be reflected through integrating anti-reflection coatings or other filter coatings. So delta doping gets you to the 100% internal quantum efficiency, and then we want to recover as much of the external quantum efficiency as possible with these additional coatings. Another way of illustrating the effectiveness of this delta doping process is in the calculations that I'm showing here. These were done by Michael Hoink, showing a calculated conduction band profile for a theoretical device that has ion implant backside passivation. So there are other techniques you could consider to introduce charge at the backside of the device to counteract this dead layer. Ion implantation, even in the best case, has a length scale in the order of tens of nanometers. So although you can improve the potential well characteristics, you're still susceptible to changes in the interface state density. So that's this DIT number. So variations in the trap density at the back surface of this ion implanted device still modulate the depth of this dead layer and lead to some of the instability issues that I showed a few slides ago. A delta layer, you can see that the x-axis has changed a lot on these plots. Now, variations in that interface state density have little effect on the conduction band profile, even a nanometer away from the surface. I'm showing here several delta layers, and this is sort of the approach that we've taken in more recent years. A single delta layer is often sufficient to achieve the improvements in efficiency that we're looking for, but multiple delta layers can help with this stability issue and help increase the conductivity of this modified back layer. So this is what we've been referring to as 2D doping or superlattice doping for essentially multiple delta layers. And so this increase in stability as a function of changing trap density on the backside has been experimentally tested. This was work done in collaboration with a company called Alacron and Applied Materials that makes semiconductor inspection equipment. They were seeing essentially a degradation in responsivity of rad-hard photodiodes used in these inspection systems when they were exposed to ultraviolet light. And so in this case, the UV light might come from excimer laser at 193 or 157 nanometers. And even at 193 nanometers, seeing a degradation eventually in the relative response of these devices for a given flux of laser illumination. The same experiment was attempted on a delta-doped CMOS imaging sensor. I'm showing in the lower left here the normalized illuminated response of one of these devices after it was exposed to 2 billion of these excimer laser pulses at 193 nanometers. And the exposure happened only in this dotted region in the lower left here. So there was no obvious change in the responsivity of this device as a function of this exposure, as plotted here on the right. So how does this process happen in the microdevices lab? I mentioned molecular beam epitaxy. This is an ultra-high vacuum deposition process. So generally, this passivation is always performed as a post-fabrication step. So we'll take a complete CCD or CMOS wafer, essentially, with completed devices, perform a backside thinning process to get down to the active device thickness that we want, and then perform this MBE process. So this is a low temperature process. We need to maintain a thermal compatibility with the wiring and other stuff that's on the front side. And then perform what's essentially evaporation, but it's sort of the fanciest evaporation you can imagine, because of the ultra high vacuum conditions, we have really fine control over the rate of silicon deposition as well as the dopant atoms that are introduced into the lattice. We've done this process in both polarities of silicon. So we use p-type doping with boron for the n-channel devices or the p-type substrates, and then n-type doping from antimony for the other polarity. And again, typically these layers on the order of just a few nanometers. So that's, again, important to maintain compatibility with that really shallow absorption depth of ultraviolet photons. The dopant concentrations that we get are pretty substantial fractions of the most dopant, essentially, that you can put into the silicon lattice in order to get the most amount of charge for this passivation process. This is a wafer scale process, as you saw on the last slide. This was an image of a wafer through a viewport on the MBE tool that we use. We can perform this process on up to 8-inch wafers, which is compatible with a lot of the CMOS fabs these days. And we've demonstrated really nice uniformity across these large areas. And that's becoming more and more important for larger and larger area detectors, some of which now are essentially consuming the entire area of a 6-inch or 8-inch silicon wafer. So the end-to-end flow would look something like this. We'd get a device wafer, typically from an industry collaborator like Teledyne E2V or SRI. We'd bond this wafer to a handle wafer, so front side down now to the handle wafer, and start thinning from the back side. So this typically involves some grinding steps and some chemical and mechanical polishing to get down to the intended device layer thickness, and then perform some cleaning steps in this MBE process to deposit the 2D doping layers, followed by what I'll describe in the next few slides as optical coatings to perform the anti-reflection functionality that we're looking for. And then various pad opening steps to expose the wire bond pads from the backside, and dicing, and we also do a lot of work in packaging at JPL as well. So some or all of these processes have at some point been done at JPL. Depending on the circumstances, some of them may be performed by subcontractors, but this is how the general flow looks. I'm going to try to morph now into talking more about the application of these optical coating layers, which I mentioned could be done at the wafer scale. So here are just some pictorial examples of wafer scale coatings, which we perform by atomic layer deposition. I'll describe what that is in a few slides. Again, with, in some cases, custom packaging. This is an example of back illuminated STA CCDs that were delivered to the WASP and ZTF instrument at Palomar as guide and focus sensors. So here they are next to the science detector in one of those dewars. In some cases, it's advantageous to perform the optical coating part of the process at the die level so that we get kind of a wider sampling of coatings to choose from for a given number of devices on a wafer, for example. So this ALD processing can be done at the die level as well, showing here the evolution of some AR coatings that I'll describe later were used for the Fireball balloon mission, allowing us to kind of optimize as we go. So let's talk a little bit about anti-reflection coatings. I mentioned how the delta doping process can get us this 100% internal quantum efficiency. So now we're concerned with the losses from silicon due to reflectance. In sort of a perfect world, silicon would have a uniform refractive index across all of the wavelengths that we're interested in. Unfortunately, it does not. As I'm showing here on the lower left, the refractive index of silicon changes quite dramatically throughout the UV. This tends to mean that there is not a one-size-fits-all optical coating that is well matched to this entire UV part of the spectrum. What that ends up meaning is that in certain bands, we can achieve very high quantum efficiencies, external quantum efficiencies in this case, by appropriate choice of AR coding, but you may have to mix and match as you move through the far ultraviolet, especially. And so this plot on the upper right here is showing a series of delta doped CCDs that were fabricated for an instrument concept that was being led by Chris Martin at Caltech that wanted to cover the far UV over multiple bands on multiple devices, essentially. And so with optimization of each of those bands with different AR coatings, we could achieve now quantum efficiencies in excess of 50% across all of the far UV. And so that's, again, combining the 100% internal quantum efficiency that gets you to the range of 30 to 40% in silicon, because as I'll mention, silicon is quite reflective in the UV, but then up into this 50 to 60% range with simple dielectric coatings. And then there's sort of an easier job of it, if you will, as you move to longer wavelengths, because as you can see, the refractive index becomes more uniform. And so for near UV, visible, near infrared options, we can consider fairly simple AR coatings like single layers of hafnium oxide or simple double layer filters that give quantum efficiencies in excess of 80% across this wavelength range. I'll talk about atomic layer deposition in a few slides, but what led us in that direction was some early work that looked at different optical thin film coating processes to deposit these anti-reflection coatings. We looked at E-beam evaporation and sputtering for some of these films. The images on the left here are showing flat field images at monochromatic illumination for devices that had different coatings on different part of the detector. So light here means that the response was increased over the uncoated regions, and dark means that the response was degraded in some way. So you can see, for example, that for E-beam evaporated coating, which may generate X-rays, which are sort of detrimental to the backside of the device, or physical damage that you might get from sputtering, the application of the anti-reflection coating, which was expected to improve the performance, actually made the performance worse. There's more evidence of this in the plot on the right, which is showing the measured quantum efficiency of one of these detectors, again, with an uncoated device showing a reflection limited response, and then a device that was coated with a magnesium oxide film, in this case, that was intended to improve the QE in this 300 to 400 nanometer range, actually degraded it substantially. And so basically what was happening was either through energetic processes as part of the sputtering process, we were causing physical damage into the delta layer, essentially, and degrading the passivation, or from that X-ray exposure, a similar phenomena. And so that led us to options that were a little bit more gentle from sort of the physical perspective. So something like thermal evaporation works. It tends to be a little bit harder to control the uniformity in a thermal evaporation process. But as I'll show in the next few slides, atomic layer deposition emerged as a nice technique for these optical coatings. It's a gentle chemical process that did not degrade the performance that we were expecting of the delta doping. And so what is atomic layer deposition? ALD is a special case of chemical vapor deposition, which is driven by self-limiting reactions of precursor chemistry that you're using in the process with the substrate you're trying to coat. And so this is a pictorial example of an ALD process for aluminum fluoride. But sort of the the magic of ALD is this self-limiting property. So you introduce your precursor chemical, in this case, trimethyl aluminum. It reacts with the surface that you're trying to coat, creating some byproduct, which is purged out in this intermediate step. And then you introduce your second reactant, in this case, HF, because we're interested in depositing this fluoride material. And it also reacts in a self-limiting manner. In other words, these species react only with the substrate and not with each other and not with the byproducts that are formed in this process. And by separating the A and B steps in this process, you get essentially perfect atomic limiting deposition for each half cycle in the reaction. So that's why it's called atomic layer deposition, but it comes with these benefits that it's a very conformal coating technique, it's very precise, and it's very uniform over large areas. You typically get a substrate temperature window that enables these reactions to proceed in a self-limiting manner, and you get extremely reliable deposition rates as long as you operate within that window, which is typically in the range of 100 to 200 C. So still compatible with the end-to-end processing. And because it's sort of this gentle chemical interaction with the surface, it does not damage the delta doping layer underneath. ALD is a pretty common thin film coating technique for semiconductor applications. It's widely used to deposit the gate oxide and high performance microelectronic devices. It's a little bit less common for optical coating applications, but there is some growing interest in using it for that. There's been a lot of work in developing basically a wide range of materials using the ALD method. So most oxides that you can think of, many nitrides, there are even some processes for metallic coatings using ALD, sulfides, and then I'll talk more about some of our ALD processes for metal fluorides that allow us to move to even shorter wavelengths. First, just a few more examples of some of these coatings. Here's an AR coating, again, that was optimized for this WASP ZTF application, which is a ground-based instrument. So an AR coating that maximized response at visible and near-infrared wavelengths. This is a hafnium oxide, silicon oxide-based coating, showing again some of the interesting packaging that was used on these devices to allow them to be budded close together. And then another application example is the Fireball balloon instrument. Here we considered more complex multi-layer coatings to optimize response in a wavelength range centered near 200 nanometers. So looking here at measured and the expected model performance of single layer, 3-layer, and up to 5-layer AR coatings considered on this mission. Early in the development of this particular project, up to 11-layer coatings were actually fabricated and tested. So here's the results of some of that work in, I lost the axes here, but these are the measured detector quantum efficiencies for the detectors delivered to the Fireball instrument, with peak quantum efficiencies in excess of 80% centered at this 200 nanometer wavelength range. Here's an image of the detector installed in the spectrograph and some of the flight data that was obtained in the last launch of Fireball. I'm going to morph a little bit now away from the anti-reflection coating and talk about mirror coatings. And it was really that initial development in the ALD processing on detectors that led us to consider maybe some other applications where the ALD aspect might be beneficial for the ultimate performance of mirror coatings in this case. So on the left here, we've probably seen variations of this plot in other talks at the UV Club. This is the increasing density of spectral diagnostic information that you encounter in the UV, particularly as you move to very short wavelengths in the far UV. This is really what motivates a lot of the far ultraviolet interest for astrophysics at these wavelengths. But this trend essentially towards the ground state transition energy in hydrogen is also tied to the fundamental reasons why the material science is challenging in this wavelength range. In other words, as you approach that ground state energy, you run out of metals that are reflective. You run out of metals that have a high enough plasma frequency that they can produce a meaningful response at these short wavelengths. So aluminum is kind of your only metal of choice to operate in these wavelength range. And you run out of transparent oxide materials that have a band energy that's higher than that ground state energy. So at longer wavelengths, you have a pretty wide selection of optical coating materials to choose from with a pretty broad range of refractive indices to choose from. So your job as an optical designer is relatively straightforward. But then as you move down into the far UV, you're left with really just a handful of metal fluoride materials that all have a relatively similar refractive index. And so you sort of run out of tricks to use in terms of the complexity of the coating, and you run out of materials to use essentially as an anti-reflective coating. So the same physics that makes this part of the spectrum interesting makes it really challenging from the material side. And so we thought that since we were working on these ALD processes, and as I'll describe, we started working on ALD processes for metal fluorides, that we could use the same processing to produce protective coatings for aluminum mirrors in the far ultraviolet. And so moving away from sort of the detector scale coatings that we're interested in, which at the wafer scale may only be 6 or 8 inches in diameter, to potentially coating things like telescope mirrors, which might be 1 meter plus in diameter. But we had reason to believe that ALD would be well suited for this task as well. It's already widely used in the display and large area solar panel industries. And as I mentioned, it's also widely used for semiconductor applications for these nanometer scale coatings. So we want to utilize these very thin coatings over very large areas, as I'll describe for this particular application. Since we're mostly interested in extending the short wavelength performance of these optical systems, we're again stuck with considering protective coatings that can maintain transparency to as short a wavelength as possible. And so again, we're limited to this handful of metal fluoride materials that we could potentially use as a protective coating on aluminum. So in order to use those materials with ALD, we needed an ALD process and the appropriate reaction chemistry that can produce them. There was previous work in the literature on ALD processes for metal fluorides, but they tended to be relatively complex from a precursor point of view. The metal organic compounds used in the processing were fairly complex, and in particular, the fluoride reactants used tended to leave residual metal contamination and required relatively high temperature processing. So somewhat incompatible with high performance optical coating. We decided at JPL to try to simplify this whole reaction pathway and use kind of the simplest fluorine source that we could think of, hydrogen fluoride. And I'll describe some of those results in the next few slides, but basically this is a simple way to get a reactive ALD process that can work at low temperature and that can yield a metal fluoride film that has low contamination and therefore low loss. Of course, for those that are familiar with semiconductor processing and have been in a clean room, HF is a fairly nasty chemical, so there are handling concerns, admittedly, to using this process, but with appropriate controls, we've had fairly good success at depositing these materials. So again, using this HF route, we've developed ALD processes for kind of all the metal fluoride materials that we're interested in, and maybe more importantly, for some of these mirror coating applications, we can deposit them at relatively low substrate temperatures. So again, materials like aluminum fluoride, magnesium fluoride, and lithium fluoride. Okay, so just a brief background on protected aluminum mirrors. So again, this is a very simple optical coating. It's a single layer of metallic aluminum, which, as I showed a few slides ago, in a perfect world would have extremely high reflectance in the far UV because of its high plasma frequency. The free electron nature of aluminum that gives it that high plasma frequency also makes it quite reactive. So it has an extreme tendency to oxidize, even in fairly high vacuum environments. And that oxide, unfortunately, is strongly absorbing in the far UV. So an unprotected aluminum layer does not make a very good ultraviolet mirror. In order to make a mirror coating, you essentially have to avoid that oxidation by depositing a protective coating on top. The one that has been the most popular choice over many decades has been protective coatings of magnesium fluoride. What I'm showing here is that even though these mirror coatings have been developed over many decades, there's still a lot of challenges in understanding the preparation of both the aluminum and the protective coating. And there's still sort of an evolution to these processes that are resulting in improved performance depending on the material. And so even in modern examples, whether it's commercial vendors or other research reports, you can get a pretty wide variation in performance for notionally the same exact optical coating. And so this is another area where we thought ALD might be able to help out, is improving the consistency and reliability of the protective coating itself. Aside from mag fluoride, there's been a lot of recent interest in lithium fluoride as a protective coating material. This enables you to operate below the short wavelength cutoff of mag fluoride, which is around 120 nanometers. Lithium fluoride has been used on previous NASA missions as a protective coating material. The FUSE mission used lithium fluoride on aluminum for the reflective coatings in two of the channels on that instrument, in order to achieve performance really only in this 90 to 110 nanometer wavelength range. You can see that at the time that the FUSE mirrors were fabricated, there wasn't a good understanding of how to achieve high performance out of the lithium fluoride itself. So although the short wavelength performance could be improved over something like mag fluoride, it was really only at modest reflectivities, 60% or so, with correspondingly low reflectance, even at longer wavelengths. Since FUSE, there's been a lot more work at understanding this problem with lithium fluoride. It really has to do with the hygroscopic properties of lithium fluoride and its reactivity with water. So that tends to result in this degradation in reflectance as a function of time after the coating has been fabricated. There's been a lot of nice work, for example, out of Goddard Space Flight Center in developing evaporation processes for lithium fluoride that essentially are done at a high substrate temperature. And this has been seen to really improve the performance over these legacy coatings. So this red curve here is an example of what they call ELIF, or enhanced lithium fluoride. But even this high temperature lithium fluoride tends to degrade as a function of time. And so some of the things that we've been looking at with ALD is one, maybe taking some of this ELIF material and putting an extremely thin encapsulation layer on it. That's an example shown in this blue curve here that has been done in collaboration with the University of Colorado. Here, using a very thin encapsulation layer of aluminum fluoride. So the idea is that the encapsulation layer is thin enough that it doesn't create enough absorption loss at these short wavelengths to degrade the performance of the mirror, but thick enough that it can kind of seal in the chemical stability in the lithium fluoride. We're also looking at sort of an all ALD approach to deposit the full lithium fluoride and cap stack at JPL. One possible advantage of the ALD process is that it maintains this low deposition temperature. Aside from LUVAR, which is the flagship mission concept considering lithium fluoride coatings like this, which they acknowledge are at a relatively low TRL. There's also some upcoming CubeSat and SmallSat missions which are baselining this coating process. The Sprite CubeSat mission, which is led by Brian Fleming out of CU Boulder, will try to use this ALD encapsulation approach with the Goddard ELIF process and the Aspera Pioneer SmallSat, which was recently selected, both again to operate in this wavelength region below the short wavelength cutoff of Hubble. Here's just some of the results of some aging studies that we've done with CU Boulder for this encapsulation process, showing the effect of long-term storage at elevated relative humidity levels over time for different RH conditions. And we saw that although these thin ALD layers could not completely eliminate the degradation, they could measurably slow it down. And so we've demonstrated this process initially on some optics that were flown in a sounding rocket payload called Cystine out of CU Boulder. And we're planning, as I mentioned, to do the same thing for this Sprite CubeSat. So this is an image of the Cystine secondary in our system at JPL, which for now is limited to the area that you see here. So we can coat optics with these ALD coating techniques at the 6 to 8 inch diameter scale. We're interested in demonstrating the scalability of this overall process to larger areas. So we have an ongoing strategic astrophysics technology with NASA to try to transfer some of these processes to a unique tool that exists at UC Santa Cruz to demonstrate some of this work at the meter class. In the meantime, we've also been creating some of these protective coatings, again, all deposited with atomic layer deposition, investigating different choices of cap material, as I'm showing in the lower right here. But even these all ALD films have advanced to the point now where we can create a coating that meets the LUVAR requirements, although again, still at relatively small scales. I'm going to skip a little bit through some of this. It's implied on the last slide that we have this issue here where although we're creating all of these protective coating layers with atomic layer deposition, there's actually not a good way to deposit aluminum with ALD. So the aluminum layer is still evaporated. It's technically challenged to consider combining these two techniques for various reasons. So to sort of cut to the chase, we've been using a process called atomic layer etching to allow us to combine evaporated aluminum for now with these ALD encapsulation layers. Atomic layer etching, or ALE, is essentially the inverse of ALD, where again, a series of self-limiting chemical reactions can now etch material one atomic layer at a time. So we can use this approach to allow the aluminum to oxidize and then remove it in a self-limiting manner inside the ALD chamber before being coated. I'll skip this as well since I'm going a little bit long, but we're interested in more complex multi-layer optical coatings as well, which would conventionally be used with a high-index fluoride material like hafnium fluoride or lanthanum fluoride. We have ALD processes for materials like this and are just starting to make some of these more complex multi-layer coatings that are useful for things like dichroic beam splitters, et cetera. And the takeaway is that although you can buy some of these types of coatings commercially, there's still a stability and performance issue. So these are just some examples of test coatings developed for flight projects at JPL or Caltech that experienced unexpected degradation, let's say, as a function of primarily, again, humidity exposure. So ALD might have some opportunities to engineer some improved stability into these coatings. One example of that type of engineering is creating mixture materials. Since we're depositing these materials one atomic layer at a time, we can sort of mix the atomic ratios at arbitrary compositions. And so that's one thing we've been looking at in mixing lithium fluoride with aluminum fluoride to improve the stability versus But in my remaining time, I wanted to get back to the detectors again, and talk about leveraging some of that work on aluminum and ALD to create bandpass filters that can operate in the far UV, and specifically filters that are integrated directly onto a delta dope detector. This is an important problem in a lot of UV sensing applications, and particularly for astronomy applications in low Earth orbit, because when you're trying to detect an ultraviolet signal, it's often right up against a pretty strong background of zodiacal light and air glow that is invisible in longer wavelengths. And so delta doping can create this 100% internal quantum efficiency across the UV, but of course that extends into the visible and near infrared as well, out to the silicon cutoff near 1 micron. So it'd be useful to develop a way to add red rejection essentially to the detector. And again, this is challenging from conventional optical coatings. There's sort of no such thing as a short pass filter which operates in the far UV because of that problem that I mentioned a few slides ago of a limited number of materials to choose from. And there's really not a material, for example, that absorbs low energy photons more than it absorbs high energy photons. Just doesn't work that way. So if you do buy ultraviolet bandpass filters that can operate, say, at Lyman alpha, you'll typically get a filter with a peak efficiency in the range of 10 to 20%. We wanted to see if we could do better by integrating these devices directly on a detector. Some of our initial interest in this work was for a high energy physics application in collaboration with Professor Hitlin at Caltech, who was interested in creating a readout detector for a barium fluoride crystal scintillator. The crux of the problem is that barium fluoride is an interesting material for this application because it has a very fast scintillation component that is centered near 220 nanometers, but unfortunately it comes in the presence of a very slow scintillation component at longer wavelengths. And so that influences timing experiments using these types of detectors. So we wanted to know if we could create a bandpass filter that would reject that longer wavelength light. And this is done with multi-layers now of aluminum and transparent dielectric materials. This is in fact often how these commercial filters are fabricated in these wavelength ranges. Again, sort of the more complex dielectric coatings are often not available as you move to wavelengths below 200 nanometers. And often their efficiency will be quite low. So here on the left, I'm showing some examples of some of these metal dielectric filters that were optimized for a wavelength around 275 nanometers, I guess, showing the effective transmission that you get for a stack on a transparent substrate like quartz, so relatively modest, 30% peak efficiency. And then the transmission that you get if you integrate the same stack onto silicon. And you can see you get more than a 2x improvement in the end-to-end transmission of these multi-layer filters. And that's sort of gets back to what we initially described as a problem, the high reflectance of silicon at short wavelengths is now an effective match to this metal dielectric structure that greatly increases the transmission that you get versus using the same stack on a transparent substrate, for example. Essentially, it's a free cavity in this multi-cavity structure. And so we fabricated avalanche photodiode devices for that physics application, again, with very low response at visible wavelengths, but maintaining this high quantum efficiency in the UV. We have developed coatings for a CubeSat mission called Sparks, which is led out of University of Arizona by Evgeny Skolnick. This is a 2-channel instrument which operates with a conventional standalone filter in the near UV, but again, we couldn't find a far UV commercial filter that could operate with high efficiency. And so we've opted to, again, use this integrated metal dielectric filter to produce a response that can even exceed the peak efficiency of the near UV channel in this case. here's one of the detectors developed for Sparks and some of the characterization data that was done on witness samples. This is just meant to show that for these filter structures, we've measured some of them now for more than a year in storage without seeing large changes in the measured reflectivity in this case. So there's reason to believe there's some stability in this multi-layer ALD approach. A couple of weeks ago, you heard from Brad Chenko at Goddard on the Dorado mission. This is also considering the use of these metal dielectric filters, again, for a band here centered closer to 200 nanometers. And then finally, we'd like to evolve this concept essentially now to either multi-band or multi-wavelength, essentially filter applications by creating either discrete areas of the detector, which might be optimized for different wavelengths. So this sort of gets back to an early slide where I argued that there's not one size fits all coding for all of the far UV and near UV. So you might have imaging applications that could benefit from a large format detectors with different coatings on different areas of the device. Or for spectroscopy applications, ideally you could tailor your coding to re-optimize the coding performance to match the dispersion of light that you're getting in your spectrograph system. And so that requires essentially changing the thickness of these materials, or maybe even changing the material itself as a function of position. For a lot of spectroscopy applications, what you really want is a continuous grading in the coating thickness. When I described ALD initially, I described one of its key advantages is its extreme uniformity. So we had to do a bit of head scratching to figure out how to get non-uniform ALD films in order to sort of maintain our existing infrastructure for coating these detectors and our existing processes and modeling. And the approach that we've adopted is this cavity approach where we can force ALD into a non-uniform mode by limiting the spatial extent to which reactant can coat the substrate of interest, basically by putting a lid on the process. So here's a cross-section view of how this works. You have your coating substrate on the bottom, and it's separated by a precision shim, in this case, some kind of mechanical apparatus to tune the height of some cavity to limit how far into the cavity the reactant can make it. This is a digital process, ALD, where you have this binary repeating AB cycles. And so you get this consistent introduction of reactant, purging, and then introduction of the next reactant, purging. And with the appropriate choice of the height of this cavity, you can create a profile that has this graded thickness effect. And so I'm showing on the right here some measured variation in film thickness as a function of distance into one of these cavities that we've used for testing, showing these profiles that can be generated. For a fixed cavity, of course, you would be fixed with the given profile based on the geometry, but it turns out you can tune this profile essentially by tuning the working pressure of the process to get either further or not as far into the cavity, and then build up whatever slope or linear profile you want by superposition of these different ALD cycles at different pressures. Of course, there are ways to create these graded thickness coatings by other thin film techniques for line of sight techniques like evaporation and sputtering. You can do this by masking or shuttering. But we think maybe there's some advantages to this approach as well, since it doesn't require these moving parts in your vacuum coating chamber. And so we've made some of these test coatings initially for a test coating operating in the visible and the near infrared that was intended to maximize the overall transmission from 300 to 1,000 nanometers. And so again, for any single thickness uniform layer, you might get a profile like the dashed lines shown in the left over here, which is relatively high quantum efficiency, but maybe at most you can get an average QE of 80% across this band. If you could tune its thickness gradually as a function of the dispersion, you could do a lot better than that with just hafnium oxide. And with a 3-layer stack, as I'm showing in the middle here, you can theoretically create a device that has greater than 99% quantum efficiency across this whole range. And so we've fabricated a coating like this. This is a measured spatial map of the change in aluminum oxide thickness in this case that's sandwiched between 2 uniform layers of hafnium oxide, and some of the measured spectra at different points along this device as you step across, showing indeed that we're getting less than 1% reflectance across this wavelength range. And this is working over a relatively large area, so centimeter scale areas compatible with a lot of the detectors we might be interested in coating with this approach. And then ultimately, the obvious next step, I think, is to combine the metal dielectric approach with this graded thickness approach to extend the performance to even shorter wavelengths, but also to kind of add this functionality of red rejection that you get from the metal dielectric filters to this increased effective transmission that you get from the graded thickness. And so this is just an example of a modeled, relatively simple 3-layer coating with only a single graded thickness layer of aluminum fluoride, and then a single metal layer of aluminum that can, in principle, create a spectrograph that has a significant increase in effective quantum efficiency versus a bare device, again, with sort of the benefits that you get from the red rejection at longer wavelengths as well. And so that covers everything. It's again sort of this. We're trying to maintain this view of all of the instrument performance that one might be concerned with. Starting from the detectors, adding in AR coatings and filter coatings, but also working on these mirror coatings now. And so hopefully getting to the point where we can move from those single-digit efficiencies up to something a little bit better. So thanks. Happy to take questions.
Okay, great. Questions, please. If you have a question, it's a small enough group, so either raise a hand or just ask the question.
So I have a question for you, John. You talked about the backside surface, the backside potential trapping electrons. Now, if we had a p-channel device that was collecting holes, presumably that potential would be working in our favor to drive the charge away from the surface towards the wells. But perhaps there are other benefits of the delta doping of a p-channel device, which is collecting holes. So I wonder if you'd comment on that.
Yeah, I think, and I think Chalet is on the line. She can correct me if I'm wrong, but actually the nature of the interface states works against you no matter which polarity you are. So even in a p-channel device, you still have an issue with the dead layer at the back. And so we solve the same problem just with the different doping. Of course, there's also the stability benefits that I mentioned in either polarity that are associated with any types of charging that might happen at the back, whether it's from radiation or other damage.
Other questions?
This is Sri. I have a question related to radiation. How this AR coating material, different material, different layer reacts with the radiation? Is it effect for the silicon layer if you go for a multi-layer or single layer or different material like magnesium fluoride or hafnium oxide something? Did you study about this?
Yeah, there are definitely things you need to be concerned with. First, one concern is that with all of these different materials that we've considered, with an unpassivated device, you might expect the interface state density to vary widely from material to material, depending on deposition processes and things like that. But the delta doping kind of takes care of that, as I showed in those calculations. In other words, we don't care really as much if the DIT changes for a different material. There are possible chemical interactions that can happen with certain materials that you have to be aware of. So we've had some experiences with coatings of hafnium oxide that can, even with an ALD approach, form hafnium silicates at the surface and consume some of the delta doping layer that would then degrade the performance of the device. And so we've gotten around that for applications where we're interested in using hafnium oxide by introducing very thin buffer layer between the hafnium oxide and the silicon. And so it's another nice aspect of ALD that we can put a 1 or 2 nanometer layer of aluminum oxide in between, for example. Other radiation effects maybe in some cases require more study. We've done proton testing on a lot of these optical coatings, and of course the expected range of protons of most energies of interest don't really interact with the thickness of the optical coatings that we're considering here. So that the cumulative thickness might be in the range of 10 to 100 nanometers, depending on the optical coating. And then again, charging effects would tend to be compensated by the delta doping, but maybe that's an area where more study is needed.
Roger, did you have a question or?
Yeah, I do. Does the delta doping also serve to address surface generated charge, dark current, that might form because of these defects at the surface?
Yeah, no, that's a good point as well. And the short answer is yes.
So
it can compensate for those types of defects that would otherwise increase dark current at the back.
So that's pretty important in the UV where our sky background is so low.
Yeah, and I don't know if an early slide had some observation of that. Maybe not, but that's something that we've studied and I believe have data on that we could show.
I'm kind of interested in running some tests to see if we can apply some voltage across detectors like our CMOS detectors in order to reduce the lateral charge diffusion. As you noted.
Roger, isn't it true that the layer is electrically conducting, the boron layer?
Yeah, yes, that's right. Because of the doping density being so high, which means that you can actually use it as a backside bias.
Right. Yep.
But it's something that I don't think has been fully explored in, conventional devices. It's been done in very thick devices where you just can't, your lateral charge diffusion would kill you because of the thickness. But on thin devices, of course, it's still beneficial because it keeps the cosmic rays compact.
So you mean to say apply a potential there so the gradient is stronger than normal?
Yeah, a small one.
Yeah, this is surely, so there is almost in all of these thin devices, there is a field-free region. So a charge will diffuse until it gets to the depletion region. So yeah, it would be beneficial. Depends on the doping that is in the epi, like how much voltage we require to deplete it. But it's definitely worth exploring. And we've done that with some of the early CMOS devices that we delta doped.
Right. Given that we're interested in making the devices very thin anyway to kill off the red response, that might not require very much voltage.
So John had a question about, as you go to FUV, in one of your plots, you had sort of a quantum efficiency was increasing because I suspect it's because there are more than one photoelectron being emitted. What are the consequences of this for precision photometry or even in spectroscopy? So there will be some change, there'll be a wavelength dependent correction.
Correct. Yeah. So this slide, or sorry, I was just there. This slide in particular shows QE that's been corrected for this quantum yield effect. And so, yeah, I didn't discuss quantum field or quantum yield explicitly, but yeah, below 300 nanometers, you'll start to see an increase in the quantum yield. So in other words, the probability that you generate more than one electron hole pair for a given photon. There are empirical relations that you can, fall back on to estimate the quantum yield in this wavelength range, but it is the hardest range of wavelengths to get an accurate number out of because of a lot of systematic effects associated with absorption loss and things like that at these very short wavelengths. So it's something that's probably best determined empirically from a fabricated device. And so there are photon transfer techniques that you can use to try to back out what that quantum yield is, but it does have noise implications. Of course, these extra charge carriers could be beneficial in some cases. If you're read noise limited, you're essentially getting extra signal at these very short wavelengths, but because it's a stochastic process, if you're shot noise limited, you're getting extra noise.
So have there been studies by astronomers worried about precision photometry as you go to the FUV range?
I'm going to say no, but maybe someone online can correct me if I'm wrong. I think there's a lot of uncertainty from what I've seen in the literature over what the quantum yield actually is in silicon, at wavelengths down around 100 nanometers, for example. But I don't think that kind of study has been done. Maybe
so the Kepler group tested one of our devices for precision photometry. Actually, the paper that they based a lot of their selling work was on our device, but it was at best near UV. And as John was just saying, it's just around 300 nanometers when you start getting the quantum yield concern. But we are trying to get this a little bit more quantified with single photon counting detectors and get a handle on it. And perhaps we could try to do that study.
Yeah, but Shule, it gets worse, right? As you go to shorter wavelength, as you can see from this plot.
Absolutely, yes.
In fact, at nominally 1100 angstroms, I know that there's 60 units to 80 units. I don't know how much of that is real versus double photoelectron emission.
Oh, this is, as John said, this has been corrected.
Yeah.
So what we did, in fact, John, I think, is that from the 2012 paper? 220, yeah. If that's the case, what we did is we did photon transfer curves at every wavelength that we have plotted here and did the correction of for quantum yield. So if anything, we were underreporting some of the quantum efficiency, trying to be conservative about it. So yeah, this is true quantum efficiency as best we can measure.
Yeah, we need to think about this though.
Wouldn't it be possible to just calibrate it, if for any brightness there may be multiple electrons being emitted, but
yeah, Mike, the main problem is, if you're like, let's say if you have 10 photoelectrons reported by the system, okay, and you don't know that it's 8 or 12.
yeah, okay.
Okay, well, that's pretty bad actually.
Yeah.
Because if it is just 10 photoelectrons, then I know exactly the statistics.
Yeah.
is square root of 10. But if you then say, oh, and on top of that, I'm going to tell you something which I only know statistically, I'm not sure that's actually worth the thing. I mean, yeah, it's good for detection. If you want to know, have you found something? Getting
Yeah.
one and a half photo electrons is better than one. I'm agreeing with you.
Yeah, no, I understand.
But if you want to say, am I doing some precision work? Then I don't think getting, oh, somewhere between 1 and 2 is good enough. In fact, you're better off having 1.
Yeah. Yeah, no, it's like adding another readout noise on top of the readout noise, but worse. Yeah.
And
I had
then
a question about the.
and maybe this will vary with the position of the sensor. I mean, I'm not sure. I understand. I mean, I need to digest this.
Well, yeah, and as Chalet mentioned, if you had a photon counting detector, you could answer a lot of these questions, explicitly. But that doesn't necessarily carry over to an integrating detector. I think a lot of the challenges you have, especially as you get down around Lyman alpha, is with measurement uncertainties, even in the photon transfer approaches, because it gets hard to generate nice flat fields there.
Yeah.
It's just difficult in all aspects.
Okay. Any other questions?
Optical interest in ground-based groups in these detectors. These are really amazing. I can imagine that the U-band has just been terrible up to now, and for ground-based. Is there any serious interest, perhaps from even LSST or something?
Shri, do you remember the interest from LSST?
Oh,
We tried.
I think I've raised a painful story.
So Mike, I'd like to, can you go to the tapered coding slide, please?
Yeah.
Sorry, I jumped in late because dinner.
Yeah, I want to point out for ground-based astronomy, one of the most exciting things is to get almost 100% QE in the 300 to 400 range for spectroscopy. Because by tuning the, it has to be a fixed configuration spectrograph. An imaging spectrograph doesn't work, but for a slit spectrograph, this is amazing.
Yeah.
And also, if you look at this, if you look at the next slide, I think it is that, next slide. Have a look at this. So the passband for any given wavelength is fairly narrow, and you could keep pushing this. And so what this does is it cuts down the scattered light in your spectrograph, because you're only sensitive to the wavelength which is supposed to be falling on a pixel, not the light that's scattering from all of the rest of the grating and optical surfaces. And so you get better contrast. So for spectroscopy, I think this is amazing.
Oh, yeah.
So that's my ambition for ground-based astronomy with this.
Is this going to be our LRIS blue detector or something, or?
Well, LRIS is an imaging spectrograph. I think you have to envisage slit spectrographs for this, but it's crying out for a high throughput spectrograph with a slit, just a long slit.
Mm-hmm.
Anyway.
Yeah.
Okay, any other questions?
So Shri, some food for thought on that whole quantum yield and multiple electron hole pairs. There might be something about the footprint of a high energy photon and the photoelectrons that it would produce versus 3 photons with a single electron production. And that's some of the stuff that we want to look at with this single photon counting detectors, and see if we can discern any difference between the behavior.
So is this like what X-ray astronomers call grade pixel? They grade each event by seeing
something like that. Yeah.
So by actually looking at the adjacent pixels and giving a grade, that would be. And there's a huge literature in X-ray astronomy on grading the pixel, grading events.
Right.
Yeah. Okay. Well, it's I'm not getting any questions from sort of the group. So thanks everyone, highly informative. I've not really understood what was atomic layer deposition. I really thought something more mechanical and not chemical. I learned something very interesting. Thanks, John. Thanks, Shulay. And good night, everyone.
Yeah, thank you.
Yeah, thanks very much.
Thank you. Good night.